So as I told you in previous video, today we'll cover two topics. First is quadruple integration method. So in last lecture we discussed about starting from external loading to a moment or directly to moment. After obtaining this moment information, after integrating twice, we can you know, obtain the elastic curve y as function of x. Instead of doing that, we today what we're gonna do is we'll begin from w directly and do quadruple integration to obtain yx. After we discussed about quadruple integration, we'll discuss about statically indeterminate problem. So you can, if you recall what you have done like back in axial loading and torsional loading and classes, we always covered statically indeterminate problems. However, for pure bending and beam deflection, we didn't discuss about statically indeterminate problems. Finally, we'll be able to discuss statically indeterminate problems because we finally learn the deflection of the beam under the bending. Okay, so let's begin from the first topic, which is direct quadruple integration method. So we'll solve two example problem. First example problem is a beam, simply supported beam with uniform distributed loading W. So W means the force per unit length, which is distributed over the entire beam. So if we recall the Euler-Bernoulli beam equation, fourth order derivative is related to W, and W turns out to be a constant over the entire region. So entire region, Wx is defined as W simply, and we can quite easily perform the integration. So we can perform the integration 1, 2, 3, 4 times, and after each integration, you're gonna have 1, 2, 3, 4 integration constant C1, C2, C3, and C4. And first and second integration, they can be connected to Vx and Mx. Okay, so here we have 4 unknowns, and it's our job to find these 4 unknowns out of boundary conditions. So we have 4 unknowns, which means that we have to obtain 4 independent boundary conditions. Okay, so let's try to get 4 independent boundary conditions. And actually, we have 2 simply supported boundary, and each simply supported boundary have where is it, like 2 boundary conditions, y equals 0 and m equals 0. So the conditions we can find is y equals 0 and m equals 0 at the left hand, y equals 0 and m equals 0 at right hand. In mathematical form, at left hand x equals 0, y equals 0, m equals 0. At right hand, or at x equals L, m equals 0 and y equals 0. Okay, so out of these 4 independent conditions, we can find 4 unknowns. So first condition, x equals 0, y equals 0, you can find C4, because if you put 0 here, if you put 0, 0, 0, 0 here, you can find that C4 must be 0. And when x equals 0, if you plug in 0 in the place of m, when x equals 0, m is 0. If you plug in 0, 0, it means that C2 must be 0. Okay, so these are we already consumed 2 boundary conditions, and we have 2 more boundary conditions and 2 more unknowns. So let's plug in x equals L, m equals 0. So after plugging L, and 0 here, so what you're gonna have is minus w over 2 L square plus C1L equals to be 0. Okay, and out over here, we can obtain C1 equals to be maybe WL over 2. Okay, WL over 2, you can obtain C1. After obtaining C1, you can use the last boundary condition at x equals L, y equals 0. So if you plug in x equals L, here, and at that condition, y must be 0. So you have a lot of terms. That's why I use this term, because when we consider m, there is only 3 terms, but when we account for yx, there are 5 terms. That's why I define C1 first and move on to the this condition. So if you plug in these conditions, and it should be resulting y equals 0, or right hand side is 0. Okay, and after plugging C1 condition, you can find the equation for C3, and C3, after massaging this equation, turns out to be minus 1 over 24 WL cube. Okay, so this is how you approach the quadruple integration method. Yeah, so after finding and identifying 4 unknowns, you have to identify 4 independent boundary condition, and out of 4 independent boundary condition, because this is the system of 4 linear equations, you are always guaranteed to find the unknowns. Okay, so after plugging all these unknowns, yeah, you're gonna you can write down the elastic curve y as a function of x. Now let's move on to another example problem. So this example problem considered cantilever beam with point force at the right end. Here what you can realize is Wx equals 0 for entire zone of the beam. Okay, so here the problem becomes even simpler. We have to consider EI y 1 2 3 4 as a function of x, and it must be connected through Wx, but Wx is 0 for entire zone. Okay, so you can do quadruple integration quite simply. So after doing quadruple integration, here you can simply plug in w equals 0. After plugging w equals 0, and you can get rid of first order term in terms of x, so you only have these terms left. So after quadruple integration, you're gonna have EIYX equals to be composed of these 4 terms. Each of them include the unknowns, integration constant C1, C2, C3, and C4. Okay, and out through this integration, after first integration, you have C1 and Vx. After second integration, you have M and C1x, C2. So simply go back to last page and plug in w equals 0, w equals 0. You have C1, you have C1x plus C2. Okay, so these are the informations we can cook up out of this boundary condition and loading conditions, and we can find the boundary conditions at left hand and right hand. At the left hand, when x equals 0, y must be 0, and when x equals 0, dy dx must be 0, because this is cantilevered beam. So we have 2 conditions from left, and from the right, this is free end, so you have m equals to 0. However, it's free end with point force. So due to this point force, V at x equal L must be P. Okay, so please be careful about the sign convention of V. Okay, so after these finding these 4 boundary conditions, you can obtain C1, C3, C2, C3, and C4. So from x equals 0 indicates y equals 0 condition. So if you plug in x equals 0, x equals 0, 0, and 0, you only have C4, and C4 must be 0. If you consider dy dx, through the same procedure, C3 can be 0. So you found that C3 and C4 are 0, which makes your life becomes much easier. Then you can utilize V at x equal L becomes P. If you plug in x equal L, it must be C1, and then must be P. Okay, so you determine C1 equals to P. Then after realizing that C1 is P, you only have one unknown, which is C2. So when x equal L, M must be 0, because it's a free end. There is nothing to support distributed compressive and tensile loading at the right end. So M is 0. Okay, and if you plug in x equal L, it becomes C1L plus C2. Okay, and it must be 0, and we already obtained C1, so C1 is P. So C2 must be minus PL. So after plugging in C1 is P, and C2 equals to be minus PL, and if you plug this in the place of C1 and C2, you end up having YX. Okay, YX equals to be 1 over EI and these 2 terms. Okay, and you can see that at x equal L, which indicates the deflection at the right end due to this force P, it turns out to be, if you plug in x equal L, it turns out to be negative PL cube over 3EI. So that will be the solution for the deflection of the beam at the end. Okay, so with this, we discussed about 2 example problems. Okay, so distributed loading and point loading. In addition to that, we can also think about more complex loading conditions. However, for more complex loading conditions, we can use this discontinuity and interface boundary condition. And because we have already considered one example problem considering discontinuity boundary condition. I only prepared these two simple example problems. Okay. However, if you want to solve more complex problem, it's your job, and you can take a look at the textbook, and you can find some example problem considering this interface issues. Okay, so with that, let me wrap up the video here, and in the next video let me move on to statically indeterminate problems.